In this presentation, we're going to look at fraction concepts which are developed in Chapter 15 of your text. For students to gain a solid understanding of fractions, their experiences with them need to begin early. According to the Common Core State Standards, they need to begin in first and second grade with partitioning shapes and referring to fractional amounts. And then in third grade, students should have a major emphasis placed on fractions, and they should start paying attention and recognizing and being acquainted with fraction symbols, and they should start exploring unit fractions. And then in fourth grade, they will move on to fraction equivalence, and they will begin completing and working with the operations involving fractions. Understanding fractions means understanding all the possible concepts that fractions can represent. And it's so important that students get experience with all the different meanings of fractions, because oftentimes we might just represent fractions with one or two of the symbols, like the part-whole relationship, where you present students with a circle and say, I'm going to shade part of it, and let's make a representation for what the shaded region represents to the whole. And that's a classic way to begin an introduction to fractions, and that's fine. But then we want to proceed and discuss the other representations, like those that are listed on the screen here: measurement, division, operator, and ratio. With measurement, you could identify a length, and using that length as a measurement piece. So you could say, I have a string that's 5/8 of a foot long, and then ask how many 1/8 could fit into that. So you're linking a fractional understanding to measurement. All students need to understand that a fraction is a division problem, that you're dividing a numerator by a denominator. For instance, when somebody is asked even to share something, like if you're asked to share $10 among 4 friends, students should be able to translate that to meaning not only 10 divided by 4, but the fact that each friend is getting 1/4 of the full amount. And in connection with division, a fraction is an operator. So if you're asked to find 4/5 of 20, that means that you would want to multiply 4/5 times 20, or divide the 20 into 5 parts and find 4 of them. So it also represents an operation. And the last one that is very, very important, and that's on the bottom of the slide, is that a fraction represents a ratio. It tells you the likelihood of something happening with a whole set or host of events, like saying there's a 1 in 4 chance that it will rain tonight, or a 25% chance. So you want students to start linking fractions to all of these, and then in turn, especially once you get to the ratio, that's going to link well into fractions and decimals as well. But these early experiences, well-rounded early experiences, very holistic with all of these different representations, are key to students gaining a very full understanding of fractions. Research indicates that there are many reasons that students struggle with fractions, and many of them stem from their trying to relate fractions totally to what they already know, whole numbers. It's important for you as a teacher to help your students see how fractions are alike and how they're different from whole numbers. An explanation of some of the common misapplications of whole number language to fractions can help. So here's one misconception that students often have. They think of the numerator and denominator as separate and not as a single value, and they need to realize that they together represent one value. Not recognizing equal parts. So for instance, on this slide, it's a little bit difficult to see, but you notice that it's partitioned into halves. However, the green on the bottom has some demarcations showing 3 triangles. So students may think that this is 3/4 green instead of a half green, and they need to realize that it's based on the scale and the fact that half of it is in each color, and those demarcations in the green don't do anything to the amount of green that's shaded. Another misconception is thinking that a fraction like 1/5 is smaller than 1/10 because it has a smaller denominator. And visuals can really help with this. Like once you show a student what 1/10 of a circle is compared to 1/5, they can grasp the fact that 1/10 is much less than 1/5. The fourth misconception is using the operation rules from whole numbers to compute with fractions. So for instance, students thinking that 1/2 plus 1/2 is equal to 2/4 because they've added both the numerator and the denominator. But again, expressing this with visuals is very helpful for then translating to the rules. There is substantial evidence to suggest that the effective use of visuals, which I mentioned in the previous slide, concerning fraction tasks is important. And there are three prominent ways to model fraction concepts. There are area models, length models, which concern the number line, and then set models. Look at all these different manipulatives that are on the screen. All of these can be employed to teach the concept of fractions through area. So the most common one are circular or pie pieces, but you can use rectangular regions. You could also use a geoboard. On the geoboard on the screen, we've modeled fourths. You can use grid or graph paper. You see that the fractions 5/15 and 1/5 or 2/10 are modeled on the grid paper, and one of those grid papers looks just like the geoboard. You can use pattern blocks. Any set of pattern blocks that you buy from an educational store have pieces that can fit within another one, so you can overlap them to show maybe 1/6, for instance. And I'm specifically thinking of the relationship between that equilateral triangle and the hexagon that is on the screen. But you can also use simple everyday things like a piece of paper and fold it into different regions so that you can represent fractions using area. With length models, lengths or measurements are compared instead of areas. And you can use either physical materials, which you would compare on basis of length, or number lines, could be subdivided. Cuisenaire rods are an excellent tool to use as a fraction length model. I really like Cuisenaire rods. They're wooden rods, and they're all related because they increase in length by 1 unit if they're stacked with each other. And you can kind of see that on the screen there. And actually, I shouldn't say 1 unit. They're specifically 1 centimeter greater than the next one as you move down the line. So the white is 1 centimeter long up to the orange, which is 10 centimeters long. And they each have a different color, which makes them very easy to identify. So for instance, if you wanted to teach students the concept of 1/6 and 1/3, you could start with the dark green rod that's in the center of the stack of Cuisenaire rods on your screen, and you could show that the red is 1/3 of the length of the dark green and the white is 1/6. In set models, the whole is understood to be a set of objects, and subsets of the whole make up fractional parts. So let's look at a couple examples. On the slide, you see 3 different set models. The first one's a little complicated because you, as a teacher, have to tell the students what number or quantity makes up the whole. So let's say that you want 12 items to make up the whole, and then you ask students to express the quantity of red counters to the whole, which is 12. Well, once they count up the red, they have more than the whole represents. So this gives them a first experience with an improper fraction. 16 over 12, which would reduce to 4/3 or 1 1/3. And they see that the red are taking up a full set and 1/3 of another set. Then you look at the set example on the right. You have 2 color counters. If you were asking students to represent the quantity of yellow to the quantity overall, they would write a fraction of 9 to 15. Or there are 3 yellow to every 5 overall. So they're starting to make a lot of connections between part and whole. And then lastly, at the bottom, you have the one with the vehicles. And you could ask students, well, how many cars to total vehicles? How many trucks to total vehicles? And there could be some great set understanding concerning fractions that could develop there as well. Here is a fun kinesthetic exercise that uses set models to teach fractional understanding. What you would want to do is start out with a specific number of students to represent your whole, maybe 6 or 12. And I say 6 or 12 because those are great numbers for working on halves, thirds, and sixths. If you wanted to work on halves and fourths, for instance, you might want to use 8 or 12. But you can invite a specific number of students to come to the front of the room, and you could say to the group, if you are wearing tennis shoes, or if you have brown hair, or if you're wearing earrings, move to the right. If not, move to the left. And you would ask the whole class, what fraction of our friends are wearing whatever it is that you specified, tennis shoes, earrings, brown hair, whatever. And you could invite them to whisper to a friend in the class and then to share with the class the fraction that the group represents. There's so many different things you could do with this group. You could change the number of selected students in the hall. You could also ask how many friends are in 1/2 of the group, how many would be in 1/4. And you could also start to connect equivalent fractions, because if students say that 1/2 of the group would be 3/6, and then you could say, well, okay, great, what does that reduce to? And start to connect the fact that 1/2 is the same as 3/6. Students will start to have a greater understanding of equivalent fractions. The first goal in the development of fractions should be to help students construct the idea of fractional parts of the whole. And that's why the area model is the first one that's usually introduced to students. The parts that result when the whole or the unit has been partitioned into equal-sized portions or fair share is something that you're going to teach in 1st and 2nd grade. It's in 3rd grade that students start to learn that a fraction by itself does not describe the size or the magnitude of the whole or the parts. A fraction tells us only about the relationship between the part and the whole. Comparing two fractions with any representation can be made only if both fractions are parts of the same size. So what am I trying to say? If you look at the slide, the picture that's on the slide, and you ask somebody, I have 2 pizzas, and you say, do you want 1/2 of a pizza or 1/3 of a pizza? If you don't specify what size each of those pizzas are, an individual really does not know if 1/2 or 1/3 of a pizza indicate a bigger portion. They have to know what size they each are. And unless they're coming from the same size, it is only then that you could say 1/2 is greater than 1/3. So fraction size is relative to the size of the whole, and that's something that you'll start to introduce in 3rd grade. You really cannot develop the part-whole relationship and the whole idea of fractions without teaching students to partition. Partitioning is simply sectioning a shape into equal-sized parts. So if you're looking at the screen, there are several different instances where we are separating each of the models, area, length, and set, into equal-sized parts. For instance, in the area model, we see that we're separating those 2 hexagons into equal-sized parallelograms. And the length model, we're taking the whole long rectangular solid, and we're chopping that into equal cubes. And then the set model is divided into sets of 2s. But interestingly enough, in all of those models, we are breaking them up into 6. So you're going to want to start introducing some of those key words that we use when we talk about fractions. Not only 6, but halves, thirds, fourths, fifths, and eighths. And you want to do this before you use symbols so that students can become familiar with the terminology. There are a couple of key criteria that must be met and therefore taught when you are instructing students about partitioning. First, it's so important that they realize that fractional parts must be the same size, though they don't necessarily have to be the same shape. And we'll see that in a moment. But with respect to that first square, the students need to realize that that figure is containing fourths, and it's not thirds, that they would need to partition the red bottom and make that into 4 equal parts. And again, the number of equal-sized parts that can be partitioned within the unit determines the fractional amount. So when students are looking at an area model and trying to determine how many equal parts can I break it up into, once they determine it, that is the fractional amount. So with the 2 connected hexagons, they'll quickly realize, well, I could divide this into halves, or I could do it into 6 equally. There's a couple different options there. A good activity to have students do in order for them to realize that the sizes of the partitioned parts have to be the same, though the shape does not, is one like that is on the screen. You could say, okay, which ones of the figures represent force and which ones do not, and explain why. Well, students could quickly realize that A and F definitely represent force because they are both the same size and the same shape. And upon greater investigation, they might realize that also E and G represent force because the partitioned areas are taking up the same size even though they're not the exact same shape. But you would want students to think even further to tell why B and C and D are not representing force. Well, in B, we see that we have both different shapes and different size, and the same goes for C. And then in D, students could see that even though they're all rectangles, they're all different sizes, but you would want students to explain their rationale. Students need to be able to partition a number line as well into parts and realize what each part represents with respect to the whole. There's a great example on page 350 of your text that helps to model this. Let's say you give students a number line and you represent a certain overall length, like saying the distance to school from home is represented as the full length from 0 to 1. And you say there's a student, Nicole, who is walking to school, and you are going to mark certain lengths on that number line between 0 and 1 and ask them to represent the fraction of the entire distance that she's traveled. Well, you could see that on the bottom number line with the mark that you placed that she's traveled 1/4 of the full distance. And you could put other additional marks as she progresses, like 2/3 or 3/4. And this is a great way for students to use the number line to understand fractional relationships. Partitioning is a strategy that's commonly used in Singapore for solving story problems, and the students tend to do very well with it there. Here would be an example of how a problem is set up and solved using partitioning. Let's say that you tell students that a nurse has 54 bandages, and if 2/9 are white and the rest are brown, how many are brown? Well, the students might model this with a bar diagram by partitioning the 54 into 9 parts and then counting up the 2 parts that they need to determine that the answer would be 12. An important recommendation by researchers to help students learn fractions is to build on students' informal understanding of sharing and proportionality. Students in the early grades partition by thinking about how can they fairly share or divide something. Sharing tasks are generally posed in the form of a simple story problem, like 4 friends are sharing 2 cookies. How many cookies will each friend get? A visual solution to this is on the right, but it's shown with the 4 friends sharing 5 pieces of pizza. And you notice that on the slide, the students have to delegate 1 piece to each, and then they have to think about how they're going to break up those remaining 2 pieces of pizza. And so they end up discovering that to fairly share it, they have to break it up into thirds, and each friend will get 1 2/3 piece of pizza. And then let's say that the students are asked to share 5 cookies among 4 friends. They do the same thing. They allot 1 cookie per each child first, and then they realize they have to break up the last one into 4s. But then there's a discovery that occurs through this visual learning, and you notice it on the screen. The student writes, I think that however many children there are, that is how many pieces you have to divide the item into, the leftover into. And that's a huge discovery. And using the visual aids and having students explain can help students progress to that level of understanding. In whole number learning, counting comes first, and this helps students to add and later subtract. And this is also true for fractions. Counting fractional parts, or what we call iterating, helps students understand the relationship between parts, the numerator, and the whole, the denominator. The top part, your numerator, represents the counts that are being made, and the bottom tells students what is being counted and how many. Counting fractional parts can be done in so many different ways. For instance, you could ask your students to count to 4/5, and they have to think about what is being counted, the fifths, and how many of them do they want to count. 4. Remember, the numerator tells you the number of counts, so they would say 1/5, 2/5, 3/5, 4/5. Students should be able to always tell how many fifths are in one whole. That would be 5/5, or how many sixths are in a whole, 6/6. Iterating applies to all models, but it can be particularly connected to length models. So for instance, you could give students like a piece of string that is 2.5 feet long, and you could say, how many fourths could we break this up into? And the students would have to visually realize that they could break that up into 10 different fourths, and they could count by fourths to get to the 2.5. Equivalence is a critical but often poorly understood concept, and this is particularly true with fraction equivalence. In the Common Core State Standards of Math, fraction equivalence and comparisons begin being emphasized in grade 3, and then they're applied in grade 4 and beyond. The general approach to helping students create an understanding of equivalent fractions is to have them use contexts and models like those that we've discussed to find different names for a fraction. This is the first time in a student's experience that they're seeing that a fixed quantity can have more than one name, and actually it can have an infinite number of names. And the area models are an excellent place to start to begin to understand equivalence. And there are several different examples of area models that are used on this slide to show students that you can have various names representing the same quantity. I really love the example of the pieces of pie, how you can have 2/3 of a pie expressed in numerous different ways, all depending on the size of the pieces that you cut. But all of the other ones, the paper folding, the grid paper, and the dot paper, also express fraction equivalence quite valuably too. Let's consider this fun activity which gives students an opportunity to explore fraction equivalence. Let's say that students are given 24 counters in 2 colors, 16 red and 8 yellow. And you can even get a little creative and say, oh, let's let the 16 represent apples, the red ones represent apples and the yellow ones represent bananas. And let's say you ask the students to group the counters into different fractional parts of the whole. And you use the parts to create fraction names for the fractions that are apples and fractions that are bananas. And again, you're expressing it to the whole. So you might ask them first, okay, write a fraction expressing how many apples there are to total fruit and how many bananas there are to total fruit. And they might write 16/24 and then 8/24. And then you could say, all right, how about you make groups of 4 within each set of fruit. So the students might realize, okay, I can make 4 sets of 4 apples and 2 sets of 4 bananas. And then when they write this as a fraction expressing the groups of apples to total groups of fruit, they have 4, 6, and then for bananas they have 2, 6. And then you could say, well, why don't you group them in groups of 3? And when they do that, they're going to end up having 2 groups of 8 apples and 1 group of 8 bananas, and they'll realize to the whole they can express the apples as 2/3 and the bananas as 1/3. But the interesting thing that students might start to notice is that the apples and the bananas, regardless of how they're written, if they're written as 16/24 with respect to apples, 4/6, or 2/3, all of those are equivalent, and they represent the total number of apples using different numbers, but they're all equal because they're all the same amount of the part to the whole. And this might be the first time recognizing this. The area model is a great visual for connecting the concept of equivalence to the standard algorithm. When using the area model, the approach is to look for a pattern in the way that the fractional parts are configured to both the part and the whole. I think that the garden plots example that's in your text on page 362, it's activity 15.19, is a great way to illustrate this concept and to help students make these connections. This activity says to have students draw a square garden on a blank piece of paper. It might even be good to give them an actual square piece of paper, like a scrapbook piece of paper, origami paper. And you begin by explaining that the garden is going to be divided into rows of various vegetables. So you might want to tell them, we're going to make 3/4 of the garden corn. And so they would initially draw 4 equal rows and shade in 3 rows. But then you might say, 2 family members are going to harvest the corn equally. So now they're going to want to partition this into 8 parts, or just cut the 4 rows in half. And then they could see that 3/8 of it will be harvested by one family member, and another 3/8 will be harvested by another family member. But altogether, 3/8 plus 3/8 is still 6/8, which is 3/4. So they're seeing that fraction equivalence occurring again, and partitioning is helping to make that concept sink in. The previous couple of examples illustrate to students that multiplying the numerator and denominator by the same constant number results in equivalent fractions with larger numerators and denominators. And we know that is the standard algorithm for creating equivalent fractions. Students need to be instructed that when we're putting fractions in simplest terms, that they are also equivalent fractions. I think that oftentimes when we use the term reducing fractions, it implies that something's getting smaller, and that's not true. We're putting it in simplest terms, but the value of it stays 100% the same. So you want to not use the term or terminology reducing fractions. And that might be difficult for you not to use, because I think it was so commonly used, at least when I was being taught fractions, and probably even from your teachers too. You really also want to accept all equivalent fractions, and do not say that an answer is incorrect if it's not in simplest terms, because they are 100% the same numbers. And that's extremely important, because otherwise students start to believe that 2 equivalent fractions are not the same when one is not reduced. And so we need to move away from what was previously taught and accept all fractions that are equivalent as correct answers. When students are looking to see whether 2 or more fractions are equivalent, they're comparing them. If they're not equivalent, students can determine which ones are smaller and which ones are larger. Very few students have strong number sense regarding fractions, and this is something you can help students cultivate by teaching them to think about which fraction is closer to 1, which one is closer to a half, and which one is closer to 0. You want to teach students that a larger denominator means smaller fractions or pieces of a pie. Let's look at the exercise that is on the screen, because I think it's fantastic. It says which fraction in each pair is greater. Give 1 or more reasons. Try not to use drawings or models, and definitely do not use common denominators or cross multiplication. Don't get me wrong, common denominators and cross multiplication are terrific and they work, but if you teach these before you require students to reason, they will never have an opportunity to think about the relative size of various fractions, and they will be less likely to develop number sense about fraction size. So for instance, check out this student's reasoning with A. When they're reasoning between 4/5 and 4/9, the student writes 4/5 is bigger because it's 1/5 from a whole, and 4/9 is closer to 1/2. So they're developing number sense. And then as you read their additional reasonings for the others, you see how this whole idea of being able to compare and visualize if something is closer to 1, a half, and 0 is developed because students are required to think more critically about it. In the previous example, I mentioned how 0, 1/2, and 1 are benchmark numbers when we're talking about fractions. These can be good to use when asking students to estimate the fractional size of a shaded area like those on the screen. They're also very useful for rounding with fractions. If a fraction is less than a half, then you might want to round down to 0. If it's greater than a half, you might want to round up. Or if it's clustered very near around a half, you could include rounding to a half. It would all depend on what your directions are. But those benchmark numbers are very useful in helping students to learn how to estimate.